14,000 kilometers of steel cables have allowed the Brooklyn Bridge to maintain its structural integrity for more than 100 years. Why can these specific strands of metal support such colossal engineering feats without failing? At first glance, the material appears to be a simple collection of twisted wires, but in reality, the internal physics allows for immense load distribution. This journey toward extreme strength begins deep within iron ore mines and transitions directly into the heat of the steel mill. Everything only gets more complicated as the raw material reaches the processing stage. Alloys are melted at temperatures exceeding 2,900 degrees to ensure the chemical bond of the metal is flawless. The liquid steel is then cast into solid billets, which must undergo rigorous technical inspections to identify any microscopic structural voids. One can notice how the red-hot metal is eventually drawn into thin wires and mechanically twisted into the finished cables. These heavy coils are then prepared for shipment to infrastructure projects located all around the globe. Steel wire rope was first developed during the 1830s within the deep mining districts of Germany. Before this innovation, hemp ropes were the primary means of hoisting, but they could no longer manage the increasing weights of industrial extraction. By replacing organic fiber with metal, mine hoists gained the ability to descend hundreds of meters underground with significantly higher safety margins. It is visible how this single mechanical shift opened the path for large-scale industrial mining operations on a global scale. The process is only gaining momentum nearly 2 centuries after its invention. 10 million tons of steel cable are consumed by the global market every single year, across sectors including heavy industry, shipping, and oil and gas. Infrastructure for renewable energy and the operation of millions of elevators also rely entirely on this material. Because of these high-strength strands, skyscrapers can rise to extreme heights, effectively shaping the architectural skyline of modern cities. It seems simple to imagine a wire supporting a load, but the technical reality lies in the ratio between a small diameter and an enormous load-bearing capacity. Bundles of tightly twisted steel wires provide the necessary flexibility while ensuring that force is distributed evenly across the entire cross-section. Therefore, a cable measuring only a few centimeters in thickness can successfully support hundreds of tons of weight. The equipment rotates the outer strands around a central core with constant tension to prevent any overlapping or structural weakness. One can notice the precision of the winding machines as they create a perfectly uniform cylindrical shape. The metal lays in a compact, spiraled configuration that resists both tension and environmental degradation. This specific arrangement allows the material to endure for decades even when subjected to the harshest industrial or maritime conditions. From the depths of the earth to the peaks of the tallest buildings, the material remains a fundamental mechanical marvel of the modern world. The finished rope leaves the winding station, transitioning into a calm stage of final quality verification. 1,500 meters is the depth some underground mines reach to begin the journey of a steel cable. Why is such a massive descent into the earth necessary for raw material? The ore deposits required for high-strength steel often lie deep beneath the surface crust, requiring complex infrastructure to reach the reddish-brown iron ore. But simple digging is insufficient for solid rock. High-power drilling systems bore into the stone with jewelry-like precision to create specific channels for explosives. Controlled detonations fracture the solid rock, releasing massive blocks of iron ore. One can notice how the dust slowly settles after the shockwave passes through the tunnels. Enormous hydraulic excavators then maneuver in the confined space to lift boulders weighing dozens of tons each. These machines load the raw material onto mine trucks possessing payloads of several hundred tons. It seems simple to move the rock, but in reality, these trucks must navigate dedicated routes continuously to transport the ore out of the pit. The process is only gaining momentum. At the stockpile area, the trucks dump the ore into massive hoppers that feed onto conveyor belts stretching for hundreds of meters. Vibrating screens and magnetic separators work in tandem to strip away dirt, sand, and coarse impurities. The pre-processed ore is frequently crushed into smaller, uniform sizes. This physical reduction makes the material significantly easier to handle during long-distance transport and the eventual smelting phase. Specialized rail wagons and bulk cargo ships take over the logistics, with each vessel hauling thousands of tons across the globe. This cycle of extraction and initial processing runs without a single pause. Such a relentless pace is required to guarantee a steady supply for the global steel industry and ensure enough raw material exists for specialized cable production. Everything only gets more complicated when the ore trains finally arrive at the steelworks. Thousands of tons of iron ore are mixed with recycled scrap metal before being fed into an enormous electric arc furnace. The structure of this furnace is as tall as a multi-story building. Inside, giant graphite electrodes channel immense electrical currents directly into the mixture. This generates heat exceeding 2,900 degrees, which is a temperature high enough to liquefy solid metal. One can notice how the metal turns into a swirling mass that glows with the intensity of volcanic lava. Transition to the next level. To give the steel its specific mechanical properties, engineers introduce alloying elements with calculated timing. Manganese is added to increase the final strength of the cable, while chromium or nickel is used to provide essential corrosion resistance. Silicon is also integrated to enhance the ductility of the metal. It only looks obvious to melt the ore, but in reality, the chemical balance determines the safety of the finished product. At the same moment, workers introduce quicklime and fluorspar into the heat. These additives form a layer of slag that rises to the surface like a thick protective foam. This slag acts as a natural filter, absorbing remaining impurities and refining the molten metal to leave the steel cleaner and stronger. Massive electrodes stir the entire mixture continuously to maintain homogeneity. Modern sensors monitor the chemical balance with absolute precision, ensuring every single batch meets exacting industrial standards. The molten stream eventually leaves the furnace, transitioning into a calm stage as it moves toward the casting area. 1,000 degrees. This is the approximate temperature the glowing billets maintain as they exit the cooling molds. Why is it necessary to transition the metal to the rolling mill while it still glows with such intense heat? The delay of even a few minutes would allow the steel to lose its thermal energy, making the material resistant to deformation. By utilizing this retained heat, the facility ensures the metal remains ductile enough for the immense mechanical pressure that follows. Continuous casting has replaced the antiquated method of pouring individual batches into separate ingot molds. One can notice how the molten stream descends into copper molds equipped with advanced forced water cooling systems. The liquid metal makes contact with the cold internal walls of the mold, causing the outer shell to solidify instantly while the center remains a liquid core. This solidification progresses steadily from the exterior toward the center, eventually forming solid billets several meters in length with square or rectangular cross-sections. Massive alloy steel rollers, some reaching diameters of several meters, rotate ceaselessly to receive the hot material. It is visible how the metal undergoes a physical transformation as it passes through the primary rolling mill stands. Each individual pass between these rotating drums applies thousands of tons of pressure, flattening and elongating the billet. But this is just the beginning. The thickness of the steel decreases as its total length increases during every transition between the rolling stands. This specific process repeats across multiple stages of the mill, gradually transforming the original square or rectangular cross-section into smaller semi-finished shapes like round bars, flat strips, or long slabs. Everything only gets more complicated as the steel moves through the line. The consistent high temperature allows the material to deform without the risk of cracking under the extreme compression. At the same time, the repeated application of mechanical force realigns the internal grain structure of the metal. This structural reorganization makes the steel significantly more uniform and increases its overall strength. The equipment gradually refines the dimensions of the semi-finished shapes before the material finally enters the wire drawing stage. The molten stream goes further along the production chain. 150 tons of steel move toward the cold rolling line after the initial hot rolling phase transforms them into semi-finished products. Why is such a massive volume of metal subjected to further compression? To the eye, the thick bars seem ready for use, but they must be drawn into much smaller wires with precise technical dimensions to meet industrial standards. This transition requires the material to undergo a calculated reduction in its physical cross-section. High-pressure water spray systems immediately engage to cool the glowing hot bars emerging from the rolling mill. One can notice how the liquid hits the heated surface, creating clouds of steam as the temperature begins its first controlled drop. The steel then enters a series of rolling stands positioned in a strict linear sequence. Each individual stand houses large alloy rollers that exert massive hydraulic pressure to gradually thin and elongate the metal bar. The process is only gaining momentum. With every single pass through the rollers, the square or rectangular cross-section of the steel is reduced and reshaped into specific round or flat forms. It is visible how the metal stretches under the mechanical load, preparing the internal structure for the upcoming wire drawing stage. Successive dies with progressively smaller diameters receive the steel as it enters the final shaping phase. Each passage through a die makes the wire thinner, the surface smoother, and the internal grain structure more uniform across its entire length. This specific stage is carried out at room temperature, yet it demands absolute control over the pulling force, the movement speed, and the friction levels between the steel and the die surface. But this is just the beginning of the precision requirements. Even the slightest deviation in tension can cause the wire to snap or lose the ductility needed for its future applications. In modern plants, laser sensors are installed along the entire length of the line to monitor the wire diameter with sub-millimeter accuracy. These sensors are paired with automatic feedback systems that adjust the pulling force in real time to compensate for any physical resistance. The result is high-strength steel wire coils produced with near-perfect dimensional accuracy and the specific durability required for industrial cable manufacturing. Reaching the desired dimensions is only half the journey. It seems simple to produce a wire of a certain thickness, but in reality, the mechanical standards of the steel must be forged through a harsh final test known as heat treatment. At this stage, the cold-drawn wire is fed directly into a furnace to be heated to extremely high temperatures, typically between 500 and 700 degrees Fahrenheit. Inside the furnace, the atmosphere is tightly controlled in terms of its gas composition and the rate of heating. One can notice how the metal turns a glowing red as the thermal energy alters its internal crystal structure. This physical transformation realigns the lattice of metallic grains to create the ideal balance between hardness for load-bearing and ductility for twisting. As soon as the target temperature is reached, the wire is guided out of the furnace and directly into the quenching zone for rapid cooling. There, jets of high-pressure air or baths of specialized industrial liquids such as mineral oil hit the steel to lock in the newly formed grain structure. The material is ready to move to the next processing phase without haste. 100% of the steel wire surface must be shielded against environmental degradation immediately following the completion of the heat treatment stage. Why is an additional layer of protection applied to an already hardened material? The heat-treated steel remains vulnerable to atmospheric oxygen and moisture, which would initiate oxidation and compromise structural integrity before the product even reaches its destination. A protective barrier, typically consisting of zinc galvanizing or a specialized polymer coating, is integrated to serve as a physical defense. This layer functions as a calculated shield for strands destined for high moisture environments, such as maritime zones or areas with heavy chemical exposure. But this is just the beginning. The wire passes through a preparatory cleaning phase where a mild acid solution strips away every trace of grease, industrial dirt, and microscopic rust. It is visible how the metal surface transitions to a pristine state, ensuring the subsequent coating achieves a molecular bond. At first glance, the dipping process looks like a simple submersion, but in reality, the molten zinc bath or polymer extrusion system requires absolute synchronization of temperature and pressure. The equipment gradually coats the moving strand, maintaining a uniform thickness that must be entirely free of air pockets or microscopic gaps. One can notice how the coated wire emerges with a consistent metallic or synthetic sheen as it moves toward the next level of processing. The process is only gaining momentum. Precision sensors, accurate down to fractions of a millimeter, monitor the diameter of the wire in real time as it glides along the conveyor system. Everything only gets more complicated as advanced automated inspection systems scrutinize the geometry for any signs of warping or subtle distortion. Because even a tiny deviation in the wire's cross-section could become the origin point of a catastrophic structural failure when the material is subjected to extreme tension. Data from every meter of the strand is continuously recorded and compared against rigorous technical standards within the digital control unit. The metal lays in an even layer on the tension rollers while the scanning lasers map the entire surface. If the system detects the slightest irregularity or a breach in the coating, the material is immediately flagged and removed from the active production line. It only looks obvious to check for surface flaws, but in reality, this final trial ensures the steel can withstand decades of service in the most demanding environments on the planet. The wire moves toward the final sorting area once the sensors confirm that its physical properties meet every required specification. Thus ends one of the key stages of steel production. 100% of the individual steel wires undergo a complete transition to the stranding line once they have cleared all preceding treatment and inspection stages. Why is the selection of the internal core performed by engineers before this mechanical twisting even begins? This decision dictates the entire structural future of the cable. A core made of solid steel creates an ultra-strong foundation capable of withstanding massive tensile loads, while synthetic fibers like polypropylene are chosen to decrease total weight and enhance resistance to corrosion in specialized environments. Massive rotating frames hold dozens or sometimes hundreds of wire spools in a fixed configuration. The stranding system operates by pulling these wires under extreme tension while the frames rotate rhythmically around a central axis. One can notice how the wires gradually form a precise helical pattern that follows a pre-designed engineering map. The process is only gaining momentum. First, the wires are grouped into smaller units known as strands, and subsequently, multiple strands are twisted around the chosen core to create the integrated cable structure. It seems simple to just twist metal, but in reality, the stranding speed is tightly controlled with zero margin for error. Moving too fast carries the risk of deforming the individual wires, whereas moving too slowly significantly reduces industrial efficiency. Automated sensors continuously monitor the twist angle, vibration levels, and the tension of every single line. If any wire is pulled too tightly or remains too loose, the system executes an automatic adjustment in real time to maintain absolute uniformity. Each layer of the cable serves a distinct and vital mechanical function. The camera glides along the machine as it winds successive layers in a compact alignment according to the digital set design. The outer layer is engineered to resist abrasion, the middle layer bears the primary structural load, and the inner layer provides stabilization for the entire assembly. This specific distribution of forces ensures the finished product is flexible enough for complex installation while remaining strong enough to endure loads of several hundred tons during real-world operations. But this is just the beginning. A finished cable cannot be deployed in the field until it receives a final protective coating of oil or specialized lubricant. One can notice the cable passing through an immersion bath or a high-pressure spraying system, depending on its intended operating environment. The pulling speed of the cable remains perfectly synchronized with the sprayers to ensure that every millimeter of the metal receives an even coating. Flow and temperature sensors regulate the volume of oil with extreme precision to keep the viscosity consistent throughout the application. The lubricants used are typically based on mineral or synthetic oils, with a viscosity level strictly controlled to facilitate deep penetration into the narrow grooves between the twisted wires. For cables destined for marine environments or those facing continuous dynamic loads, the oil mixture is reinforced with specific additives. These chemical components provide necessary oxidation resistance and create a shield against electrochemical corrosion. This final stage is critical for preserving the mechanical performance of the steel after the intensity of the stranding process. The coated cable moves toward the spooling station, completing this phase of the manufacturing chain. 100% of the cable's structural integrity must be verified through destructive testing before it is deemed fit for industrial application. Why is such extreme mechanical stress applied to a finished product? It seems simple to rely on the quality of the raw steel, but in reality, internal stresses and microscopic voids can only be revealed by pushing the material to its absolute physical breaking point. The testing phase begins as large-scale hydraulic tensile machines grip the steel strands with immense force. The cable is pulled continuously with increasing pressure until the metal reaches its true load-bearing limit and eventually snaps. Cyclic bending rigs then subject the material to repeated twisting and flexing under varying atmospheric loads to simulate years of service in severe environments. One can notice how the micro-rain sensors detect the slightest change in surface friction during these maneuvers. Any sign of irregularity, ranging from microscopic cracks to minor inconsistencies in structural uniformity, results in the immediate rejection of the entire batch. Only the segments that withstand every one of these rigorous simulations are cleared to move forward toward the final packaging stage. The process is only gaining momentum. Automated systems then feed the approved cable into a high-speed industrial coiling assembly. The winding speed and tension are continuously regulated by a central controller and sensitive load sensors to ensure the wire does not slacken or overlap unevenly during the spooling. A rotating turntable works in perfect synchronization with a transverse guide rail, placing each loop of cable precisely into its designated groove. On advanced production lines, high-resolution cameras and displacement sensors are integrated to detect and correct any winding deviations in real time. It is visible how the metal lays in an even layer as the spool grows in diameter. diameter. At the end of the winding process, the cable ends are secured firmly with heavy-duty hydraulic clamps. Traceability codes and comprehensive batch data are printed directly onto the coil core for future identification. Each finished coil is then mounted onto reinforced steel or engineered wood pallets, which are then tightly wrapped in heat shrink film or industrial-grade oilcloth to provide a barrier against moisture. Everything only gets more complicated as the logistics phase begins. Automated cranes lift the heavy pallets into the ceiling storage area with calculated movements. Forklifts eventually move the units to the logistics zone for final dispatch. The coils are loaded onto flatbed trucks or placed inside specialized containers equipped with anti-roll compartments to prevent movement during transit. From a raw block of metal to a high-strength steel cable, every step stands as proof of precision and technological power. The material is now ready to leave the factory and enter the global supply chain. This concludes the final stage of the manufacturing process, ensuring the product reaches its destination in peak condition.